Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I guess we'll get started. So it's a pleasure to have Payman Mahasul from the University of Calgary speaking today. So Payman's done work in different areas of crypto, but probably is most well known for his work on efficient, secure multi-party computation. And I guess today he'll be speaking about DFA evaluation.
Thanks, Eddie. Okay, guys. So this is kind of a recent result. So this is the first time I'm preparing the talk, so it's not very polished. So please stop me if something doesn't make sense or you have any questions about the protocol. I'm hoping, because the protocol is very simple, I'm hoping everyone kind of can understand how it works. And this is a joint work with Salman, who is a visiting PhD student. He's visiting me as a PhD student, and Saeed, who is my PhD student also. Okay, so I guess I'll just start. So before, I know everyone knows DFAs, but I thought it might not be a bad idea to remind everyone what they are. So deterministic finite automatons, everyone probably has heard of them in their complexity theory class maybe, or if they have done some hardware class, sometimes they show up there. There are other names for it, finite state machines, or finite state automatons and so on. So there's different names people use depending on, I guess, the applications. They're a very simple model of doing computation. They're often used in digital logic, designing some specific hardwares, designing sometimes in computer programs, or as we'll see, sometimes designing algorithms such as pattern matching. So they also get used in designing efficient algorithms and so on. So they have other applications too. But we're going to mostly focus on their applications in pattern matching and intrusion detection systems. Is what I'm going to go into more detail about. Okay. So here is how they look like. What you have is input string, can be a bit string or from any alphabet, and then you have a set of states. Some of them are labeled, the ones with two circles are essentially labeled as accepting states, where if you end up there, you accept the input string, otherwise you reject it. And the way you decide how to move around is essentially based on the bit string. So you read the first one, you decide based on these edges, where to go next, and so on until you're done with your input, and then you decide whether you accept an input or not. Okay, so that's roughly how finite automatons work. I mean, a bit more formally, you have a tuple of Q, which is the set of states you have, these circles that I showed you, sigma, which is the set of your alphabets. This is what your input strings are from this sigma, right, this string of characters. Then you have a transition functions, which was the edges in that graph that you saw. It tells you from each state with a specific character in the alphabet where you go next. So that's delta. This is called transition function, and then you always know where to start with your input string. This is your starting state, and a subset of the states which are accepting states, where if you end up there, your string was accepted. Okay, so essentially this is the language where you say DFA accepts an input if you end up at essentially says you end up at an accepting state when you're done with processing that string. Okay. These are fairly standard stuff. Yeah, so again, the language, which is that the DFA accepts, is essentially the set of input strings that end up in accepting a state when the DFA evaluates them. Okay, so you also have a language associated with a DFA. Okay, so I think. Besides that, really, I mean, that's all we really need. And there's two main types, like in applications of DFAs that you look at. One is where you want to really know if a string was accepted or not. So it's a binary output that you're looking for, or that each of these accepting states might have their own labels, right? So the different accepting states have different labels, and you really want that label depending on where you end up. So and they have their own names, kind of. And then so for the latter, you can think of it as a classification program, right? Where the label tells you how you classify a specific input, right? So that's another way of looking at it. So for the protocols I'm going to talk about, it works for both cases. It doesn't care which type of DFA we have. Okay, so far so good. Yeah. So here is the now problem that we are looking at. And then you can think of it in both directions. Like so here is our client, small laptop, and then we have the server. You can think of the input string being held by a client and the DFA being held by the server. Okay. And this is kind of, and then the goal is for them to evaluate the DFA on that input string and let the client learn the output of the computation. Okay. As for in IDS applications, this is that I'm going to look at. This is essentially the case where it's the server who is holding the DFA. So what happens is that the IDS server has a rule set that it compiles into a DFA, which is going to be rather large. So you have a large DFA. But the inputs are relatively small, so you have an IP packet that you want to analyze. Okay, so usually the input string is smaller, the DFA is larger in the IDS application. But you can also have the opposite, and this is kind of the case in pattern matching applications where you have a really large long text, okay, and you have a small pattern. And what happens is that you turn this pattern that you're searching for in this long text into a DFA. And this pattern is small, therefore the DFA is also going to be relatively small, but you have a really long text that you want to search this pattern in. So it's like where your server is holding the input string to the DFA while your client is holding the DFA. Okay. Here, like client server essentially is whoever has the bigger input is the server for us, right? Because he is going to be doing most of the more work probably. And so this ends up being the case in pattern matching applications. Okay. So anyway, so it's not always the same. Like in Oblivious DFA evaluation, you can have both cases. Make sense so far? Yeah. Okay. So the security requirements are security requirements of the standard definitions of security for two-party computation. You want to hide, intuitively hide the DFA, hide the input string, but let whoever is supposed to learn the output, either one of these parties, to learn the evaluation of the DFA on that specific input, but nothing else. So that's the intuition, and essentially what we're going to specifically achieve with our protocols is that if the person who has the input meaning the bit string is malicious, essentially we can guarantee simulation-based definition of security, the standard ideal versus real world definition of security. For the DFA holder, what we can achieve is essentially if the DFA holder is malicious, we can only achieve privacy, input privacy. So this is an indistinguishability notion of privacy for the input holder's input. Okay, if the guy who holds the DFA is malicious, you can strengthen this and get also simulation-based security, but then you lose the efficiency, at least which is kind of what I'm mainly interested in this work, right? We want to get something that is efficient. Okay, so makes sense. Essentially, that was all I was going to talk about with the security. Yeah, we get yes.
What do you lose by not having the simulation?
What do we simulation? So essentially, if the DFA holder tries to evaluate something that is not a DFA, I, as an input holder, would not realize this, right? Still, he would not learn anything about my input. So I keep my input private, but he might compute some other function. I'm not necessarily able to verify he did this, right? Yeah, that's the problem. And adding this verification essentially kind of makes the client has to do now much more work, at least the way with efficient tools, right? Kind of that's what happens. Okay, so privacy and pattern matching. just to maybe motivate why this is interesting to look at this problem. I'm not, I guess, going to spend a lot of time talking about it, but there's a few programs that look at, most of essentially people have looked at secure pattern matching before, and mostly the motivation is there's different programs collecting DNA data and then making them accessible to different organizations and institutions to study these data. And whether this data is kind of sensitive, reveals personal information about individuals, that is the motivation for looking at Oblivious DFA evaluation when you look at pattern matching, right? There is the CODIS program, this is Combined DNA Index, but this is the FBI program essentially where, this is a code where it lets you basically use this for forensic reasons, right, this DNA data. And they often anonymize this data, but the question is whether anonymization is enough, right? So you don't know which individual, for example, this specific piece of data came from, but this is, it has been shown that even if you don't know this, there is ways to learn very well, like exactly who this, for example, DNA belongs to, or like which location, or what sort of some other physical properties you can learn from the DNA information. So there is reason for trying to keep as much of it as possible private. There's also other non-government projects, international projects that just try to collect genetic information and make them available to actual researchers. So this, for example, this HapMap project has files for download for researchers if they want to do a study on DNA data. Again, so I guess no one is really trying to keep things private at this point, but maybe at some point, if these schemes are feasible, people will care enough to do it. Yeah, so again, DNA data potentially leaking personal information, and anonymization really is not enough in most cases. Okay, so the second application is privacy and intrusion detection. Here, imagine you have an IDS. So, think about zero-day signatures where you have attacks that come in, and IDSs are actually fairly eager to come up with signatures for zero-day attacks, right? Or zero-day vulnerabilities, even if there is no attacks yet, right? Because this is kind of an advertisement, anyways, and also it prevents if future attacks come in, their customers are protected against them, right? But one problem is with when you have these signatures and you give them to your customers, then you're also revealing some information about the vulnerability itself. So there is definitely motivation, and in fact they have some, I think, ways, I don't know exactly, their own ways of kind of hiding how these signatures look like when they kind of send it to their customers. But I don't know what sort of techniques they use. But essentially they're aware of the sensitivity of this type of information. This much I know. And again, so there's motivation for hiding whatever signature set you have, or at least a subset of them that might be sensitive, right? Hiding the signature set that you have, or rule set that you have about the attacks. There's also, motivations because some of the systems are proprietary. They don't really want to reveal their types of algorithms, and they want to keep it private. So there's that reason too. There's and at the same time, clients don't really want to also. There's personal information in clients' data. Emails, files, network traffic, so on, that is private. So there's reason for the client side to also want to keep their inputs private. So these are kind of the motivations for why in these two different problems you would be interested in a solution for Oblivious DFA evaluation. Okay? Does that make sense? Yes?
Do you imagine the client uploading their files to a server, or how would that work? Do I get the DFA and evaluate locally on my files?
Well, it depends on the protocol. Depends on how the protocol works. So in our case, it ends up being that I get the DFA essentially and evaluate it on my side. But it's like an encrypted version of the DFA. But you could imagine a protocol that works in the other way, as well. But here, I guess we're kind of assuming, so any Oblivious DFA protocol would fit here. Okay, so there's definitely general purpose solutions for doing this, right? This is secure two-party computation, essentially, we are looking at. So there's general two-party computation, two main approaches. We have garbled circuits, approach, and then we have, if you want to look at arithmetic circuits and use homomorphic encryption with limited homomorphic properties, strong homomorphic properties, and so on. So there's definitely ways to do this using general techniques, but there is the drawback is, I guess, a few things I can think of. First, the circuits that you have to work with can get big really fast with, for example, DFA evaluation. Also, coming up with these circuits can be cumbersome if you don't use the general compilers. But maybe, these things you can overcome with really optimizing your circuits for this specific problem. But the other thing with circuit evaluation, with the garbled circuit solutions, is that you don't have this client-server effect, right? So essentially, both sides have to do the same amount of work, proportional to the circuit. So that's probably one of the main things that you wanna avoid. But anyway, so these are the reasons to look at the special purpose protocols, and people have actually done this, right? There's quite a few now works that look at either pattern matching or actually oblivious DFA evaluation with applications to pattern matching mostly. And so I'm not going to enumerate all the different works. Marina also, I think, has a paper that looks at this protocol. So essentially, there are protocols for oblivious DFA evaluation. There's oblivious branching programs where you can also represent the DFA using a branching program. Not exactly for a specific length input. You can represent a DFA for a specific length inputs as a branching program. So you can use those protocols as well. But again, one of the main drawbacks that in all this. Everything that I've seen so far in the protocols is that the number of public key operations is fairly large. So it's essentially it grows with the size of the DFA, and as we will see, in especially IDS applications, the size of the DFA is really big. So and this can get expensive really fast, right? So you really want to minimize the number of public key operations you have to do in your protocol. So that's the main drawback. And in fact, so the goal is we want something that is more practical, right? And there are some lessons that we can learn, I guess, from the garbled circuit implementations. There's now quite a few implementations of Yao's garbled circuit protocol, different papers trying to optimize things, get things to become practical. And there's a few really nice properties about Yao that I feel are important in getting it more practical. One is that the number of public key operations that you have to do is either small or you can get it to be very small. One is that in its design itself, the number of public key operations you have to do is proportional only to the input, not the circuit size. So that's already a nice property. That's not true about many other protocols. And then you can use OT extensions. Essentially, all the public key operations you have to do are oblivious transfers. And then there are OT extension techniques that let you then do a small number of OTs and then extend it to do many. So essentially, you do a few number of OTs and then you get many OTs for free. For free meaning that for the rest you have to do only symmetric key operations, not public key operations. And it really, initially when Fairplay was designed, actually the number of OT was cited in the paper as being the more expensive component of garbled circuit computation, but now OT is really not an issue in the garbled circuit operations because the future implementations really use this OT extension and really saves a lot of computation time. So that's one nice property that it has. So I think it's really important to make the number of public key operations as small as possible. And then there's all kinds of other specific optimizations that really pay off. What has happened with Yao was particularly Mariana gave a talk on this fast Yao's garbled circuit paper, this recent result, where they try to avoid this memory usage issue with Yao's garbled circuit protocol by evaluating each some gates and then throwing them away, don't storing them, and then do more gates and so on. So really looking at the memory usage was important, and looking at problem-specific optimizations was also important, where you could use less gates, less garbled inputs. Some operations could be done in the open and so on. But this kind of works for specific problems you look at. So looking at optimizing things for specific problems was also part of getting more efficient protocols. Okay, so with that in mind, I guess we kind of look at it for a Yao-like approach for Oblivious DFA evaluation, but so that we don't have also the drawbacks that I mentioned. First, we don't have to come up with a circuit. Second, we can get this client-server effect. All right, so here's the rough idea behind the protocol. We start with a DFA. The DFA holder starts with a DFA. He turns it into a DFA matrix. This is a fairly simple data structure for evaluating the DFA. Then he garbles the DFA, right? And essentially he does that by permuting different rows and encrypting them in a special way. And he essentially sends this garbled DFA matrix to the client. So this is essentially like encrypting the DFA and sending it to the client, as you were asking. And then they do some oblivious transfers for the client to get his garbled inputs, and then he can actually evaluate the and ungarble a specific path on this DFA matrix and recover the final output. Okay, so I mean, it looks very similar to Yao, the general form. All right, so now I'm going to just try to explain the protocol in more detail. So here is the first step. You want to go from DFA to DFA matrix. This is fairly straightforward, natural way of representing the evaluation of an input on a DFA, right? So here's your DFA. You come up with a matrix that is Q by N. So this is Q is the number of states you have, and the N is the size of the input that you're evaluating, and essentially so here's with a state 1, a state 2, and so on, numbered in some order, and then you keep moving on a path on this matrix until you get to the final state, right? So essentially this is how you present your DFA evaluation as a DFA matrix. Okay, so makes sense how this is. So these numbers are essentially, if you're at the first state, which is S1, tells you if you have a bit 0, you go to the second state. If you have a bit 1, you go to the third state. Okay, so you have a pair that tells you where to go in the next row. There's 2 indices to the next row that tells you where to go next. And this is kind of how you move on the DFA matrix, right? So you have a pair of values at each.
So if the input alphabet has size 1 and 2, you will have, sigma tuples.
Exactly, yeah. So this is for binary alphabet, and then, however how big the size of your alphabet is, you would have a long two. That's right. So see, for our IDS application, we have 256. You have ASCII characters, so it would be 256 tuple. Okay, so this makes sense. So this is very simple representation of the evaluation. And then, the final state tells you, okay, if you have a bit 1, you go to accepting a state. If you have a bit 0, you go to accepting a state. If it's a 1, you go to a non-accepting state. So it just tells you what's the final output instead of any index to the next row, right? This is for the final row. That tells you whether your input was accepted or not. Okay, so we start like this. So far, DFA matrix is size n times q. Each cell holds 2 indices. So you get 2n q log q bits to represent the whole matrix. Log q is for indexes to the next row. Essentially, you need log q bits to represent each index. And then, evaluation is just traverse a single path on the DFA matrix. Okay, so the next step is you want to permute things. Okay, first thing we want to do. And so essentially what happens here in this step is I permute each row independently using a random permutation. This permutation doesn't have to be a uniformly random permutation. It can also actually be a random shift. But, yes?
Maybe I'm missing about the matrix. Should all the rows be the same?
All the
rows?
Yes. Here it would be the same, right? So essentially this is the first state and the first row, the first state in the second row. And here before the permutation, everything is the same. Yeah. Oh, sorry. Yeah, you're right. So it has to be 4 from. Yeah, that's right. Good point. Yeah. So right now it's the same. It will change when you permute things because you permute each row independently. Right. So you randomly permute this row. So what happens is here 2 and 3 will go to whatever. So to this row, let's say I don't know what this index is, and it also will point to the permuted indices of the previous two elements, right? So this permutation matrix essentially tells you for each row how you permute things, so that's holding this information. So when I say per 2, 2 means what is the permutation of value 2 in the second row? What is the permutation of value 3 in the second row? Okay, so essentially you have a permutation matrix that tells you how to permute your original DFA matrix, and you also kind of update the indices so that they are the right indices for the evaluation. Okay, so it makes sense how this permutation matrix is built? Yeah, so it's just permuting things and updating these values so that the evaluation still makes complete sense, right? So if I still evaluate things, I get the right output using this permutation matrix. It's just that my starting state will be different. I start here, but still when I use these indices and the bits to evaluate, I get the right output, right? So far this is how this one works.
Sorry.
Yes.
In the first column,
Mm-hmm.
this state, you get this input, you move there.
Mm-hmm.
What is the second column? Is it two inputs or?
It's the second state. So each column is for a specific state in your DFA. So it means
And then what are the rows? So there's
the rows are the input. Each character in the input string
I see.
that is going to be fed to the DFA.
And then what are the two outputs in the
These two. So
state?
essentially, these you mean?
Yeah, 2 and 3.
So here it says if
character.
if you're in the first state and the input string you read is a 0, you go to the second state in the next time. If the input you read was a 1, you go to the third state. So here I assume that this was
like a 3-dimensional array: state, input, and another input.
State input. No, that's right. Yeah. So the real values of the inputs. That's right. So you can think of this pair as a second dimension, a third dimension, of size 2. Yeah. So you could think of it as being 3-dimensional. That's right. So it's q by n times 2, right? And if you have the longer characters, it's whatever size of your alphabet is. That's right. Okay. So now that you have your permuted matrix, you want to encrypt it. Okay. Still. Okay. So some things are hidden by this permutation, but there is still a lot of structure of the DFA that is being revealed. So what you want to do is encrypt it. So what you do is you generate a pad matrix. This pad matrix essentially has a random value at each, uniformly random value at each element in that matrix, right? And you apply a pseudo-random generator to each element separately to kind of expand it to the appropriate length. We'll find out what the exact length is. Okay, but essentially it's like a one-time pad encryption of the permuted matrix, right? Using a random pad matrix. Okay, so to make sure, so you don't exactly really encrypt these things, what you encrypt is the following. So you have the two indices, plus you concatenate to each a pad, okay? And this pad is essentially what you need to decrypt whatever next state you're going to go to. So it's the pad for the next state that you're going to be visiting, and this is going to be concatenated to whatever index corresponding to it. So this pad corresponds to pair 3, 4. So if it's here, it would be the pad right here. Okay? So you have two different pads for each of those. So you concatenate those to the indices, and then this is what you will encrypt using your pad matrix. Okay? So make sense how this is? So the intuition is that if I would get to this encrypted DFA matrix, what I want to be able to do is, so everything is encrypted. So I see something encrypted. So let's say for the starting cell, I know the path, so I can decrypt. But now I want to know where to go. So I get the index. I go, let's say, here, but I also want to be able to decrypt this element, so I need to know the path for this next cell. So that is what gets concatenated here. So I get to see the path too. Yes? What is it?
Don't things grow if then you doesn't encrypt the next index with something?
So that's why they don't, right? So essentially, that's why we use the PRG. But essentially what happens is the paths are fixed length, and then my PRG has to give me an output of this length, which is let's say 2 log Q plus 2K, essentially. Yeah.
So that's the seed, not the pad.
Pad is essentially the seed. Yes, that's right. Yeah. So maybe the better name would have been the seed to the PRG. Yeah. But that's right. Yeah. Okay. So make sense? All right. So now we're almost done. So that was essentially the encrypted DFA matrix. But so there's some extra things for so that the input holder can actually ungarble some things, right? How he can ungarble a specific path on the DFA matrix. So then you have this key pairs, right? Set of key pairs that the server generates for each input bit of the client. Here I'm assuming it's a binary input. Then what you need to do, so this C0, C1 is the result of the encrypted matrix that I showed from the previous slide. So what I do now is then just do a XOR. I do C0 XOR by the, so for each row I have a different key, right? I take the key pair for this row and I just XOR each of those ciphertexts with the corresponding key, okay? So here's just an XOR. And I do this for every cell in the same row, I use the same key, okay? So I'm reusing the same key. And this is essentially what happens. Yes?
I think the keys are separate from the pads you're using.
That's right, yeah. These are independent, random, yeah. Different. Okay, so and this is essentially the end of the garbling the circuit. Okay, so makes sense? Now, what happens is the bigger protocol. So what happens, for those key pairs, we will do OT, like the same way it would happen with YAO. So the client gets the keys here, right, corresponding to his input bit. This is his input string. And then, so what happens is that the server uses those keys, the pad matrix and the permutation matrix that I gave you, talked about, and generates a garbled DFA matrix. Okay, so these are essentially all what he needed. And so he sends this garbled DFA matrix plus a pointer that says, okay, here is your starting matrix, starting cell. Here I can shift the things upside down, so I'm starting from here now. It used to be the bottom, but essentially, so it says here's the starting state, you start here. So it tells the client to start here. So, and this is essentially what gets sent to the client, and the client will be able to use the keys that he has to, for each cell, exactly decrypt one of the pairs, and then, so for the starting state, he also gets the pad that is encrypting it. Okay, so really, this could be sent in the plaintext, and then essentially, yeah, he decrypts one of the pairs in here, gets the pad and the pointer to the next one. Again, uses his other key, decrypts this, uses the pad and the key to decrypt this, get the pointer, and so on. So he moves on a path on this garbled DFA matrix, and he can exactly only ungarble one element, one cell in each row. Okay, everything else looks uniformly random to him based on this thing that we've made. And at the end, there is his output sitting here, which is the final result of the computation. Okay, so that's roughly the idea. And we show that essentially this is secure. So the client, based on the security definitions that I told you, as long as the oblivious. So here you need, as long as the oblivious transfer is secure, and you have a secure PRG. These are the two things we need, right? And if the oblivious transfer is secure against malicious adversaries, you get security against malicious clients, simulation-based definition. Essentially, this is a property, but so for the DFA holder here, we don't have any type of verification of this garbling happening in the right way. So that's why we don't get the verifiability on the DFA holder side. But that's roughly the protocol. Yes?
Doesn't the client also have to do work that's proportional to the size of the DFA? He has to read the entire DFA.
No, he doesn't have to read the entire thing, right? So he only has to read the path.
So where are the rest of the elements then stored?
So I mean, so if you think about, storage. So that's interesting. Yeah. So if you consider storage as cost, then you're right.
Because if you put that on you could potentially keep that over there, but then.
So in fact, he doesn't have to store it. And in fact, we don't store it in our implementation. I'll talk about it. He can actually throw away everything and just receive, right? Even he's receiving, he doesn't really have to store things, right? He can just get the cell that he's interested in and throw away everything else in each row. Does it make sense?
As he's receiving.
As he's receiving.
So do the evaluation as he's receiving the garbage.
Yeah. So in fact, that's what we do in our implementation. We do because we don't want him to store. Just for memory reasons. This is essentially what we do. But yeah, so if a storage, you cost storage as part of, I don't know, computation, then this is not, you still have to do work proportional to the DFA matrix. Yes?
So how many Oblivious transfers do you do?
Just as many as the inputs of the client's inputs.
Okay, and one is, each Oblivious transfer is 1 out of what?
What is that?
The OT is 1 out of...
1 out of so your alphabet size.
Okay.
Yeah, your alphabet size. I'll talk a little bit more about how actually we implement this in our implementation also, because the alphabet size can be big. But yeah, so the storage cost, yeah. So it's, anyways, so the way we implement this, yeah. So you get this stream, and then you just take the one that you want, you throw away the one. So memory, maybe you don't use the memory. The communication is still large, right? If you so that's an interesting question whether you can reduce it. But I think it becomes a more fundamental problem if you want to reduce communication and still keep the efficiency, because then you might end up using peer type of solutions. Then you lose the efficiency in terms of like the public key operations not being too much, right? But in our experiments, communication was really not a factor actually. But I mean, in some scenarios, it might become a big part of the actually running time. But in our setting, it wasn't. But I guess that's something that the protocol is kind of weak. You have to kind of. Okay, so makes sense how this works. So the complexity, the public key operations are O of n on both sides. So both the server and the client have to do O of n. N is the input to the DFA. Okay, and using OT extensions also, you can reduce it to only doing K, where K is your security parameter. So think 80. Okay, public key operations. Okay, I'll talk a little bit about when you do 1 out of sigma OTs, how can you also do this. It's fairly simple, but I'll mention this. Then the DFA holder symmetric key operations is proportional. Essentially, it's n times q PRG evaluations. He does 1 PRG for every cell in the matrix. Okay? And the input holder has to do n PRG evaluations, 1 for every cell on his path. So his computation. There was some XOR, also XORs I'm ignoring, I guess, but PRG. Essentially, n times q also XORs, or 2n times q XORs. And then the communication is this many bits, it's n times 2 times n q log q plus k, where k is the size of the seed to the PRG. This many bits gets communicated. Around complexity, you can do it in 1 round, right? If your OT is 1 round. Okay, so now let's look at, so it makes sense so far? Yeah, so let's look at some applications and I'll talk about implementation as well.
So the second K was for the, what was that
this
thing?
one? This was essentially the seed to the PRG.
So it's different than the K up there?
Good question. So I guess it could also be, so yeah, that K is for the OT extension. That K actually is a statistical security parameter. So whatever, like if you want 2 to the minus K security there, you use that K, whatever you want. So we used 80. We used 80 for both, but I mean really, this one is a PRG seed. That one is a statistical security parameter. So you would have to, for your system, decide what to use. But yeah, you're right. Probably should have used a different notation. Yes.
So you said that you're going to do this in 1 round, right? So the client basically retrieves everything up front, right? So the client needs to know what to retrieve. So, I mean, I'm just not clear about the permutation. So you're not permuting if there's permutation applied to the cells, right, of the matrix, that the client would know what to retrieve. Is it correct?
The client would know what to retrieve. The client gets everything. He just doesn't keep all of it. So which one are you talking about?
So you said that there's the complexity is one round.
Yeah. So essentially it's like, so the client sends an OT query, and then he gets back the garbled DFA matrix plus his OT answers. And then he can do the evaluation on his own.
Okay, so what is the gain as a part of OT? And I guess.
What is the gain?
Well, what's the client is gaining as a result of the?
Oh, those keys. These keys are essentially what he can retrieve from decoding the OT answers, right? And he needs them for garbling. Okay, so he needs the first one. He needs the first one to ungarble the first row. He needs the second one to ungarble this element, and so on. So that's what he needs the OT answers for. But so there's no permutations that he needs to know about. Okay, so that's all he needs to know is these keys. The permutations are kind of.
He doesn't need to know, right?
What is that?
These two things he doesn't need.
He doesn't need to know the permutation matrix or the pad matrix. He will learn the permutation and the pad for specific cells he wants to decrypt as he evaluates.
Okay, so basically he learns one element that corresponds to the input character, right, for each cell in the matrix.
No, actually he only learns it for this specific element so he knows the key he knows one key for each of these.
Right, so he learns one key but doesn't know, he'll try everything and see which one.
Yeah, so he can't because he doesn't know the pad for these other different cells. There's an extra randomness that he doesn't know anything about. So it still looks uniformly random to him, even if he knows the key. So that's why we have the padding as well. And so everything is not just encrypted using the random keys, right? It's the pad plus the keys. So he only learns the pad for this specific cell. So everything else looks uniformly, essentially random to him, even if he knows the keys for the corresponding key. Yes.
Sorry, did you say there was an additional focus transfer to get that initial pad?
So no, the initial pad you send it. It's essentially you don't need to encrypt the starting cell. That's the idea. Yeah. But just since I want to kind of describe everything in general. Yeah. Okay, so we now talk a little bit more about the applications. I think they're kind of interesting. So pattern matching, you have a small pattern, you have a large text. What you do is you want to use Oblivious DFAS evaluation for doing it. And there's three different variants I kind of want to briefly go through. Is first, actually the first one I don't think I go through it, but you might want to know whether a pattern exists in the text or not. You might want to know all the locations where a pattern appears in the text, or you just might want to count the number of times a pattern appears in the text. This is, I think, the more common variant that I've seen in the papers is you want to learn all the locations, but I haven't done an exhaustive search, but this is the more common one. Okay, so essentially the output of URL after is different. So here is how the KMP actually algorithm works. Essentially this is an algorithm for doing pattern matching, and it uses DFAs. So what happens is here, imagine you have here your text, and this is the pattern you have, right? So you can create a DFA that tells you whether this pattern exists in the text or not. So how does this DFA work? You start from the starting state. Essentially, you says if you get an A, you go. So here is your pattern: A, A, B, A. So 6 is the accepting state. This is essentially your pattern. So this is if you had all the right characters, you would go all the way in. At each state, if you get a B here, this is you're just starting, so you don't go anywhere. You keep being here. If you get an A, and then here, so the first character matches, and you get a B, you go back because you kind of ruined the pattern. But if you get another A, you go to the next state. Again, here you have AA. If you get an A, you haven't ruined your pattern, but you just haven't added anything. You still keep the AA, but if you have a B, you go to the your third character also matches. You move forward. So essentially, this is how the DFA is made for a specific pattern. So DFA only depends on the pattern. Okay, so don't need to know the text to create the DFA. Okay, makes sense? So that's how this DFA is constructed. And then if you evaluate the text on the DFA, once we get here, I guess once you get to a final state, you kind of don't move anywhere, right? So this is not quite exactly what we want for our DFA evaluation, but essentially you move to accepting a state once you meet a pattern in the normal. Ignore about privacy, right? So this is how this would work in practice. So now, so this is kind of just telling you an evaluation of the text, this text. So I think I'm going to skip this because it's fairly simple. So tells you that here was the match. You get to a 6. So now let's say if you want to know the existence of so if you want to know the existence of a pattern P in a text, here's what we kind of have to have for our Oblivious DFA evaluation. For no matter what you get next, you kind of want to stay in the same state. You kind of keep looping in the same state, right? Here you just learn the existence of a pattern in a text T. Okay, so that's what you have to do. If you want to learn the locations of all the patterns in P, what you have to do is essentially you have to do a few things. First, here is how you build you change the DFA. So here, if I get an A, so here I get to an accepting state. If I get an extra A, because I had an A and A, I'll go back to the state which was kind of where I started with 2A. So I move back to this intermediate state. If I get a B, I'll have to go, I have an A, and a B, so I'll go to this state, which is AAB. State. Okay, so you just so that you start the process again. So this way, you kind of for every time the pattern exists in the text, you go to the accepting state once. So that's what happens with this type of DFA. You also kind of have to modify our DFA, garbling DFA a bit, so that as I am evaluating the DFA matrix, essentially what I have to do is for every accepting state in this row, I have to let the client know he has reached an accepting state during his evaluation, right? Because he will reach the accepting state many times during his evaluation. So I'll just have a bit indicating whether he reached an accepting state or not. And this is this is before encrypting, before permuting and garbling everything. This is kind of in the plain text data. So when he ungarbles and he looks at the plain text data, he will know whether at which locations his pattern essentially occurred in the text. So this is, whenever he gets a 1, he knows, okay, the pattern just occurred right here. That's what he learns. Okay, so that's essentially how the second variant would be implemented using a DFA evaluation. Now, the slightly more interesting version is where you don't want to reveal the locations, you want to just count the number of patterns. Okay, and so this one is. So this wouldn't quite work, right? Because here you're revealing all the locations where the pattern is, and number of times the pattern actually appears in the text is a fairly good measure of how important this. It's like a frequency test, right, for a specific pattern. So it's something as actually people are interested in. So how would you do this? And so here's the idea. So first, the server, when he's creating the circuit, he generates n different uniformly random elements in a finite field. Okay, he adds them up to get their sum, and then what happens is for every element that is not an accepting state, he just uses the corresponding random s. Okay, that he generated up there. But for each row wait, did I miss something? I'm sorry, so this was a S1 through SQ, not S1 through Sn. I made a mistake. Okay, so he generates a random element for every state. Now I'm confused. Okay, so
there's only one accepting state in each row.
Yeah.
All of those can be S2 plus 1. So if you count that, the difference will tell you how much count is there. How
Yeah,
many
yeah.
ones?
So, is it right? I kind of got myself confused with the solution.
Yeah, so if you went through this thing, you had 2 ones. So you have to count how many ones are there. Right?
Yeah, yeah. Yeah, that's right.
Just shifted it
How many
back.
other- you need as many SIs as the length of the input.
The length of the input. So this is right?
Yeah.
Okay. So why did I think? You know. Oh yeah, right. Okay. No, but it's okay. So got it. I see. So for non-accepting states, you just use the S2 for the. Okay, I'm just I guess explaining the talk to myself. You know. Everyone understands except for me how this works. But yeah, so for non-accepting elements, you just use S2. But for the accepting elements, you use S2 plus 1, right? And then you just do this. And so yeah, the client, when evaluating, he gets these values, right? And what he can do is essentially what you just said. He adds things up. He also gets the sum S. He subtracts it. He gets the count. Okay, so that's how he gets the number counts. And essentially to make sure. So you want to show that this he doesn't learn anything else besides the count by seeing these SIs that he reveals. And essentially, so what you can show is that given the count, he can really generate this. Something with the same distribution himself. So you can actually show that. It's not too hard to show. But that's roughly the idea. Okay? So that distribution essentially only depends on the number of times the pattern occurs in the text, but nothing more. So that's the... and essentially what this protocol is a protocol for counting the number of times an accepting a state is visited in an input evaluation. So one application is this pattern matching, but maybe there are some other applications. So, but it's just modifying the way you look at DFA evaluation. But that's essentially what this technique does. Okay, so makes sense? Yeah? Yes?
How would it work if there are multiple accept states?
Essentially, it would count all. Well, yes, because essentially, so what you would do is for each accepting state, you would use S2 plus 1. So yes, it would just count the total number of accepting states. If you're interested in a very specific accepting state, then you would just use S2 plus 1 for that state. So I guess you can customize it in that sense. But yeah.
If you want to track how many times you visited multiple different acceptance states, you would need to have S1, S2, and then T1, T2.
That's right, yeah. So you kind of have some sort of counter for each. Yeah. But then you wouldn't know when you were on the client side which one it was, right? So you would have to, which one of those it is, like to do the subtraction correctly is essentially. So I don't know if it would work.
I think you could. You would just scale them differently. Scale each count differently.
Yeah, but the client doesn't know which is which. Is this what I mean? It reveals extra information to him if he knows which is which counter. Like at this row, he saw a specific accessing state. At this other row, he saw a different one. I mean, at least at this point, we're protecting. I mean, we're not leaking that type of information. But if you leak that, then
You just permute those numbers. Then it's like 1, 2, 4, like that. You just do 4, 1, 3, like that. Then you will know. Instead of even adding 1, 1, 1, you add different numbers there.
Oh, I see.
And then permute them so that then you will know.
No, but he still wants to subtract these things, right?
He has to subtract S only, but he subtracts S, but he kind of, if you visit that 1 multiple times, you kind of split that up by 1, 2, 4. I think if you use those things, then you will be able to separate out how many 4s you got and how many 2s you got.
I see, yeah, so you use kind of a different base. Yeah, makes sense. Yeah, so maybe there's a, yeah, so maybe something like that would work, essentially. Okay. Yeah, so makes sense. So I don't know how much time I have, but I wanted to talk a little bit more. Is it okay? I'll use 10 more minutes. Huh? Yeah. Okay, so with the IDS application, so you have the IDS server which holds, let's say here we assume he holds a private rule set, And then the client has some suspicious data, and he wants to analyze his data on the ideas. So here is kind of an example of 3 different rules from a Snort's rule set. Or here, like the main components are, this is it says which rule set it's coming from: SQL, web, vulnerabilities, and so on. You have 2 main fields that we are interested in. There's a header component as well. This is for the actual payload. Let's say that you look at if you have, let's say, IP packet. You search for a content. So this is essentially pattern matching. This is the pattern that you're searching for. And then here is a regular expression. This is a Perl compatible regular expression, PCRE, essentially. This is what it's done. So here you have a regular expression that says if this sort of thing appeared in the data, this is also what I'm looking for. Okay, and then that's the attack description and so on. So this is how the rules kind of roughly look like in a Snort. Okay. Yeah, so, and then essentially what we do in our implementation is you can take each of these regular expressions and turn them into a DFA. There is a standard way of doing this. Okay, so you can do this. This is just some examples for 2 different regular expressions, how you turn them into a DFA. And then for the content field, as I mentioned, like we use the pattern matching DFA, right? So you can also turn any of those patterns into a DFA. So what you get is for every rule, you get a DFA. Okay, so combine those 2 things. So you get a DFA for each rule. And then there's DFA combiners that you can combine multiple DFAs into one. So we use this DFA combiners first because these combiners can let you get more efficient DFA as a whole for the whole rule set. And at the same time, you don't want to evaluate each DFA separately because this might reveal extra information. Like when you have one DFA, you just get the final output of analyzing the whole rule set. Then we also run a minimizer on this. So there's DFA minimization algorithms that let you shrink the size of your DFA as much as possible, so to get the number of states to be minimal, right? There's a few algorithms. These are not particularly efficient. This is DFA minimization is in general expensive. But this is kind of what happens offline with ours, right? This is just creating the DFA. But we do that in our implementation. There's nothing new here. We just use the standard algorithms. So here's some numbers for you. So we looked at different number of rule sets and then corresponding DFA. So this just tells you the number of signatures, essentially rules we looked at. This is the DFA size, number of states in the DFA. This is before minimization, and this is after minimization. This other one tells you the number of edges in your DFA. Okay. Oh, so here your alphabet is no longer binary. Here is ASCII characters. Okay, so you can notice, a number of edges is not this times 2 or something, right? So here you have 256 characters potentially as in your alphabet. So you have large edges, but it's quite it's relatively sparse. So this is not a very dense DFA necessarily, and we are not taking advantage of this. Anyways, but I think that's just an interesting question. But roughly here is what you get. So DFA minimization gives you a factor of 2 improvement in your efficiency because our efficiency directly depends on the size of the DFA, right? So roughly we get a factor of 2 improvement here. Yeah.
So I'm curious why you're counting the transitions, right? For DFA, you have to have the complete transition function, right? It has to be defined for each character, for each input.
Yeah.
Right?
No, yeah. So we don't really. So my point is actually that we don't take advantage of it. So you're right. But I think if you can take advantage of it, leak some information, but take advantage of the fact that you have a not too dense DFA. You can get significant improvement in efficiency. That's why I put it out there, but we don't. Yeah, you're right. It doesn't affect our efficiency at all. This the number of edges, but it would be interesting to actually get something. The reason is leak something that seems reasonable. We can quantify and take advantage of this density. For example, let's say if you have a bound on the degree, what can you do? It's even not clear, even that simple case, exactly what you can do, what sort of information gets leaked.
Also, if there is no path for you to go, right? You learn where you stopped, where you failed.
There is no path for you to go.
Right.
Well, yeah, so we have this, I guess, this loop thing that you can add so that you kind of move. You're not going anywhere in reality, but you kind of are moving.
I mean, the potential way, right now the sparse, you're not taking advantage of sparse matrix. If you could represent that DFA matrix as a sparse matrix representation, then the number of transitions could be taken advantage of. Right? If the whole matrix was represented, sparse matrix representation, I suppose it's just a table lookup the way it looks right now.
Yeah. So you have to be careful about what gets leaked.
Yeah, it may leak.
Yeah, that's the challenging part. But there
may be sparse metric implementations where the transitions it would be proportional to the size of the
exactly. Yeah. So that would be great, like some sort of solution. I think it makes significant improvement in efficiency of the protocol and the communication. I mean, the communication gets affected by this also directly. Okay, so just a few things about the OT. So here we have 1 out of 256 OT, right? And we have to do it n times, where n is the input size. N is roughly, the things we test for is 100 characters to 1,000 characters. Sometimes but it could also be bigger. So essentially what you do is there is this Naur-Pincus construction. This is not the famous 1 out of 2 OT one, this is where you can reduce 1 out of n OT into log n 1 out of 2 OTs plus some symmetric key operations. Okay, so what happens here is essentially we need 8 OTs for 8 1 out of 2 OTs for every 1 out of 256 OT, and then if you put all of this together, you have 8 n 1 out of 2 OTs you need, and then you run the OT extension on this 8 times n 1 out of 2 OTs. So we end up only needing still k OTs. K here is 80 statistical scenarios. So you need 80 OTs plus symmetric key operations. Yes?
Is it now just doing each one bitwise, or is there more to it?
Which one bitwise?
Is it going 1 out of n to log n?
Oh, this is the one where you do log n OTs, like where you get these keys.
So it's basically just doing the bitwise transfer.
Bitwise. Oh yeah, that's right. Yeah, that's right. Yeah, that's the one. So here we need 8 bits to index one of those. Yeah. But since then we can nicely combine this with the OT extension, it buys you quite a bit, because so that's essentially, known tricks, but it makes essentially OT not be a factor in our costs. Okay, yeah. And then, similar tricks with the Yao's-Garble circuit, like I mentioned. So the way we implement this, because the DFA matrix can still get pretty big, so the server just generates one garbled row. So right now the way we do it, and then sends it to the client. Client just takes the one element he needs, throws away the rest, ungarbles that one, keeps it. And then they just do it for each row. And this is essentially how we implemented it, because we had original implementation was not like this, and we had memory issues. But here, essentially, memory is not an issue at all. Like, we don't even use 1% of the RAM or anything. So there's, again, this is a big, at least implementation-wise, it saves us a lot. So that's, again, one other thing we did in our implementation. So we ran these experiments on 2 machines of fairly standard PCs. We have 1 gigabit Ethernet connections for them, and then we used snort rules for our data sets. And essentially, these are, I guess, a bunch of numbers. Here, I just played with the number of signatures we study. This is the client time. It says client online time, really, but client is always online, so this is client total time. Client time is very small. He only has to do these OTs. Essentially, it stays constant very much. Like he has to do K public key operations. So these are milliseconds. But servers, you can see, still can get big. At least in our standard PC machine. So 300 seconds, right? When you have like 80 signatures. This is where client's input is fixed. when we take a 126 character, this one, and then this is the number of signatures that is increasing. 126 characters was kind of the average for, we looked at Snort's HTTP rule set, and this is kind of the average HTTP packet size from some studies that we looked at. Here is where you really, we fix the server's rule set to 50 signatures, and we kind of play with, yes? Yeah, so that's right. So essentially everything. So this is actually ignorable, compared to this one. So I would just look at the total. So the whole garbling thing can be potentially done offline if you know the rule set, right? It's just that you don't know the client's input. So all the garbage. So this essentially leaves you with doing the OTs, 1 out of 2 and 1 out of 256 OTs of online.
But the offline time, is that all stuff you have to redo every time you get new input, or is that some of that just based on the server's input?
No, yeah, you have to do it essentially, but the only thing is that the same with YAO is that where you just you can pre-compute many of it maybe before knowing the actual inputs. Yeah. But you cannot reuse it garbled data.
So it doesn't include you're talking about DFA minimization,
yeah, even yeah.
Your DFA or whatever, is that in there, or is that?
So that's a good. Yeah, it's right. No, DFA minimization is not in here. No, because that you can do one time, as long as
you said you were using a gigabit Ethernet connection. So your communication looks like though it's going to dominate everything on here if you were actually doing this across the internet.
Yeah, so that's you probably know better than me if that's true. Yeah.
Those sizes will dominate all of this.
Yes, and we did not try to do any optimization on this, and that's essentially one of the interesting questions. I mean, still, if you look at, I think I look at the YAO implementations of this, it's even worse. It's much worse than actually what we get if you do this with YAO. But that's the problem with this security party computations. And looking at the fact that you have not too dense of a DFA matrix, that's one potential way of reducing communication. So that's an interesting question, whether you can reduce the communication, or at least
communication occurs if the whole DFA is stored in the client, then the communication only occurs during the OTs.
That's right, but you only can kind of right now use it only once, right? This garbled DFA, because you kind of so it's interesting. So whether you can reuse this garbled DFA matrix, or at least parts of it, that would be interesting. Because if you remember, you only ungarble a path on this DFA matrix, not the whole thing. Unlike YAO's garbled circuits, where you have to ungarble the whole circuit. So if you can reuse even partially the garbled DFA matrix, I don't know of a way. I mean, a nice way of reusing it would be, then you can save on communication.
I mean, it seems that even if you use it twice, you learn parts of the DFA.
Yeah, exactly. So that's how you can.
That's really bad.
Yeah, unless you change the way you garble things. Yeah, but you're right. I don't know how much you can save.
And what is this? So if you take a DFA and then you want to convert it into a circuit to be used for YAO, what is the size relationship between the DFAs?
Oh yeah. So I think I have some.
Okay.
So, but was there any other questions? I'll go to the
okay.
Your question next slide. Yeah. So. But yeah, I mean, I would be interested to see if you have any comments on the communication or. But generally, these things are kind of big, with even YAO's implementations, pretty big. This one where we change the client's input, fix the server's DFA. So client's time increases a bit because you just now have to do more OTs on the client side, but it's very, so client's computation, it's safe to say that it's really fast here in this protocol. Okay. All right, so here is your question on comparison with YAO. So essentially we did, we first tried to use, Tasty and to actually implement our protocol. First, we try to use fair play. Fair play actually crashes essentially on everything that I've tried with. But Tasty doesn't do that. But it has a bug that doesn't let you actually look at like vectors, garbled vectors, and we have reported this. Again, we were not able to actually implement our protocol using Tasty, like unless we want to manually like write a script that generates a code for Tasty so that Tasty can then like. So you had to do something. So there was a bug that seems to be. So anyway, so we were not able to actually implement the real thing, but still we were able to use Fairplay as a compiler. So that component of Fairplay works fine. So we can give a DFA evaluation code based on their language and compile it into a circuit, and then we use just the timing reports that Tasty gave us to see roughly what they get. So essentially, they use a very similar machine to ours, slightly stronger, like maybe specs than ours, but this is essentially how close we can get to a comparison. We come up with a circuit size for DFA evaluation based on Fairplay compiler, and then use their timing reports. Tasty has a table that says for this circuit of this size, this is our essentially this is what we have, right? And then for Yao's garble circuit, really that's all that matters: circuit size and input. I mean, you don't have, so maybe that's okay. So for Tasty, here we can look at so you were asking about the communication. So here we have 56 megabyte, and this is essentially what you would get with 6. So it's these circuits can get really huge for like even just doing DFA evaluation. There is this paper that Mariana presented. This is the Usenix paper. Again here you have to create your own circuit, right? So you cannot. And we didn't have enough time at least yet to do it because it just came out their software recently. But again, they also report on being 10 microsecond per gate computation. Again, using a machine that is very similar to ours. Again, slightly maybe stronger specs than ours. And this is, again, the times. The times are better than what you would get with Tasty, but it's still significantly higher than ours, both in communication and computation. Yes?
So the intuition is that because you know something about the structure of computation, you know it's DFA, you can more directly encode the computation, I guess, rather than doing it at bit level, you're doing it at the sort of DFA transition.
That's right. So that's part of it. Yes. I guess essentially that's it. Yeah.
It's not necessarily an insecure function ablation if your DFA is the function, right? You actually don't know the function you're ablating, so you have to blow it up so that you're doing the matrix lookups all the time.
Yeah. So essentially, I mean, we don't consider DFA to be the function when we compile. So DFA is the input. One part is input. Yes.
The Yao circuit size changes remarkably little. It might as well be a constant.
Which one?
It goes from 227 to 233 or things of very different sizes.
Yeah, this is not. I know what this is. This is 2 to the. 2 to the 20.
I'm sorry.
So no, you're right. Yeah, so it's 2 to the 20. So this is the that was the two. The next two digits are the power.
Yes.
Yes. That's a good point. So again, like I know Mariana knows better. Like for example, the fast garble circuit, they get some improvement because they look at when they look at specific functionalities, right, in the size of the circuit. But how large is this factor? I think it's like a factor of maybe 2, 3, or something like that. When they the size of the circuit, yeah,
About
30%. So we did not. I mean, but like I don't know how much optimization you can get with circuits for like DFA evaluation. But with 30% or so, your times are pretty high. So still, it's worth looking at. I mean, Yao doesn't solve, I guess, everything. Everyone knows, I guess. If you look at the specific functions that are really interested in you, there's big gains in looking at the specific functionalities. Okay, so a few things. Maybe we discussed kind of a lot of it. IDS DFAs are not too dense. Can we do better using this fact? I think that's really interesting, both communication and computation. The other thing is you often have to do this DFA evaluation many times. Can you do things better? Can you have better amortized cost here? Like save on the communication or the computation somehow. I mean, the same questions apply to YAO, but maybe here there's something you can take advantage of. Yeah, so better communication, especially if you can reuse part of this DFA matrix, would be great. I don't know whether it's possible or not, but that's the one thing that is I see being different from YAO is that you don't have to ungarble the whole DFA matrix as opposed to YAOs. And the other thing is, okay, so if you don't, if you want to update your rule set, can you, and let's say you have pre-computed a bunch of these DFA matrices for specific rule sets, can you do that with, I mean, do you have to do this over? Because the way we kind of create the DFAs is right now from scratch. But maybe there's a clever way of augmenting things. It's not clear how you would do it using our construction, at least I don't see it, but the rule sets get dynamically updated, so whether you can do things more efficiently. If you haven't pre-computed a bunch of garbled DFA matrices, haven't used them yet, but you want to now update them to your new rule set. I think that's an interesting question too. I guess that's it. That's all I had. Yeah. Okay, thanks. Yes.
So yeah, works with general functions, and you can transform it into something that verifies general functions. It seems like would the same transformation work here? Because it seems like you have sort of the same style approach.
Yeah, you're talking about your technique, and right?
Just like in YAO, you end up with a unpredictable value at the end.
That's right. Yeah, you can do that. Yeah, you can. I mean, right now we don't do it. Yeah, you're right. Yeah, I think you can get the verifiability property that you would get with YAO. Yeah, I think so. Yeah. Oh wait. Well, the thing is not quite. Is it true? Because I don't create the garble circuit myself as the client in this setting.
Sure, but you can imagine the client creating the garble circuit first.
Oh, so it's in the case where the DFA is, let's say, public. It's just that you're computing a DFA, you mean?
Yeah, you want to outsource the computing of
a DFA. Okay. Yeah, then yes, that's right. Yeah.